So in the last section, we limited ourselves to considering a situation where the temperature was so high that the probability of having two particles in one state was negligible. What about the situation where multiple particles could enter the same state? And indeed, this is something where the restrictions of quantum mechanics become very important. So this is at lower temperatures where quantum interactions need to be considered. Now we once again have an ideal gas, so we don't have to worry about interactions between particles, but we do have to worry about constraints on the occupation number of a state. So as we saw in chapter 2, any number of bosons can go into the same state. So the occupation number, n sub r, can be 0, 1, 2, 3, and so on up to infinity, subject only to the constraint that the sum of all the occupation numbers, n sub r, must be the total number of particles in the system. In the case of fermions, we are limited to having 0 or 1 particle in each state. I've often talked about 2, but in that case I have referred to systems with a spin, electron spin for example, in which case one state corresponds to spin up, the other state to spin down. So separating out those states and talking about them as distinct states, the occupation number can be only 1 or 0. This problem turns out to be very easy to discuss if we go to the Gibbs distribution that we discussed earlier. And if you remember, this gives you the distribution as e to the beta mu n minus beta e, with the appropriate partition function being the sum over these Gibbs distributions as a function of n and e. So using the Gibbs distribution shown in the slide on the left, we can write out then the probability of finding a particle in a state described by n particles with energy E sub r as the Gibbs distribution as shown here. Now in fact I've written it out explicitly for particles n1 in state E1, n2 in state E2, where there is a chemical potential mu associated with adding particles to the state. I've taken it to be the same because this is an ideal gas. One can write both the numerator and denominator of this expression as products of individual single particle distributions. This is simply because the product of two exponentials is an exponential of the sum of the arguments. So doing that then one arrives at the probability as a product over all states now of this factor. So let us turn then to the single particle thermal average occupation number. Remember that the partition function will follow, or the probability of finding a particle in a state will follow both from the partition function and the product of all of these expressions for all particles. So looking at the single particle term, it has two possible values. For a single state, we can have n equals 0 or n equal 1 for the case of fermions. So the partition function then just becomes, in the case of n equal 0, 1, and then we add to it the term for n equal 1, so here is the complete partition function for a single particle. The thermal average occupation of that state is then given by the sum over the occupation numbers times the probability of a particular occupation number, and that is then just this occupation number here, 0, times the probability for 0 energy, of course doesn't really matter, plus 1 occupation number times e to the minus beta mu minus e, all over the partition function that we wrote up before as 1 plus exponential beta mu minus e. So let's write that expression down again. It's on the slide. The thermal average occupation number of a single particle state for fermions is given as follows, where the bar means the thermal average. Let's make it the ith state. Now this looks a lot like the Boltzmann distribution. In the case that this exponential, and let's just simplify by considering a state with chemical potential equal to 0. In the case that this exponential is much bigger than 1, and this of course is just the Boltzmann distribution. However, in the case where this quantity approaches 1, the distribution gets severely modified. The next slide shows a plot of this distribution for beta, or 1 over beta, kt, expressed as various fractions of mu. So you see, for kt is a very small fraction of mu. This would be the low temperature limit. By low temperature, I mean kt being a number much smaller than mu. The distribution looks like this. It is 1 fully occupied until one reaches an energy equal to mu, and then it falls to 0. At temperatures above 0, the distribution smears out. And this point here, where the state is on average half occupied, is called the Fermi energy, almost exactly equal to the chemical potential. This distribution has many important consequences because in metals the density of electrons is so high that the states are occupied all the way up to a chemical potential of many electron volts, which means that even at absolute 0 of temperature, the kinetic energy of electrons in a metal is very high. In the case of bosons, the calculation is a little different. You are directed to problem 323, which I hope you will do, or at least look at the solution in Appendix M. To do this, sum for the single particle partition function, but now with a constraint that n can run from 0 through infinity. So we have to sum this partition function over this range. You need to remember the expression for the sum of a geometrical series. And when you do that, you arrive at a slightly different expression for the thermal average occupation number of a single particle state for bosons. All that changes is this sign here. This, however, has a very significant effect. At high temperature, once again, this becomes like a Boltzmann distribution. But at low temperature, there is a tendency for particles to pile up in the lowest energy state. One manifestation of this, for example, is the operation of a laser. Photons are bosons.